Okay, so on the previous video, we talked about the most important trig identity, the Pythagorean identity. So in the next couple videos, I'm going to introduce some other identities that are less often seen, but you should still be familiar with them as you move into calculus. So the next one we're going to look at is these are called the angle, sum, or slash difference identities. There's actually 4 identities here. So starting with the sine of A plus B, if I want to find the sine of the sum of 2 angles, then it's going to be the sine of angle A, cosine of angle B, plus, because I use the top sine here, plus the cosine of angle A times the sine of B. If I wanted to do the difference of those 2 angles, the sine of A minus B, then it's going to be the same thing, but I'm going to use the minus sign since that's below. Same thing for cosine now. Cosine of A plus B would be cosine of B, cosine A cosine B minus sine A sine B. I'm using the minus because that's the top one. And then if I wanted the difference, A minus B, I'm going to be using the addition sign there. Usually I like to provide a proof or a derivation of identities if it's not too terrible. These particular ones are a little bit harder to see. I'm sure if you search online for a proof of these, if you're interested, you could probably find one that makes sense for you. But I'm not going to do it here. Instead, what we'll do is let's just check this out and make sure it works by using 2 angles that we know how to find the sine and cosine of, and they actually have a nice sum. If I let A be pi over 3 and B be pi over 6, let's think in degrees for a moment. Remember, pi is 180 degrees, so 180 divided by 3, this is actually 60 degrees. 180 divided by 6 is 30 degrees. So if I'm doing A plus B, I'm actually doing 60 degrees plus 30 degrees, which means I'm actually finding the sine of 90 degrees. So the sine of pi over 3 plus pi over 6, I'm going to use the identity, but let's just acknowledge that this is the same as the sine of 90 degrees, also known as pi over 2. And we know how to find the sine of 90 degrees, or pi over 2, because that puts us on our unit circle. That puts us right up here. And on the unit circle, sine is literally the y coordinate. So the sine of 90 degrees is 1. So this whole thing should come out to be 1. But now let's use the identity and make sure we get that. So using the identity, with this being A, this is B, we need the sine of pi over 3 times the cosine of pi over 6 plus the cosine of pi over 3 times the sine of pi over 6. Fortunately, for both of those angles, we can use the same special triangle that we've been using for the last few lessons here. If this angle is pi over 3, this angle has to be pi over 6. And the sides are root 3, 2, and 1. I'm just going to be referring to this triangle for both of these. The sine of pi over 3, from pi over 3, I have opposite over hypotenuse, root 3 over 2. The cosine of pi over 6, I have to switch to this angle. And the cosine from here, the adjacent side is root 3, and the hypotenuse is 2. So the cosine of pi over 6 is also root 3 over 2. Plus the cosine of pi over 3 back to here, adjacent over hypotenuse, 1/2. Sine of pi over 6, now I'm back to pi over 6. Opposite over hypotenuse is also 1/2. Root 3 over 2 times root 3 over 2 is root 3 times root 3 is 3. 2 times 2 is 4, plus 1/4. And of course, 3/4 plus 1/4 does give me 1, which is what we were expecting to get. So it does work, at least for those 2 angles. And in fact, it works for any 2 angles. So one thing you can do with these identities is you could find, I told you were responsible to knowing how to find the sine or cosine of any angle that has to do with a special angle. pi over 4, pi over 6, pi over 3, even if it's a reference angle. But you actually can also find the sine, cosine, and tangent of angles that are not really on our list of angles you're supposed to know how to find, to know by heart, I should say, from using a special triangle. But you can still find them out without a calculator. So here's how I could do it. If I was asked to find the sine of 15 degrees, I could realize that 15 degrees is really the difference between, you can do it either way. That's either 45 minus 30 degrees or 60 minus 45. Either way, you're going to get 30 degrees. Let's go with 45 degrees minus 30 degrees. Because those are two angles we know how to find the sine and cosine of. And using my identity, with this being A and this being B, that's going to be equal to the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. 45 degrees, that's using the other special triangle. 45 degrees is pi over 4. 1, 1, root 2. So sine of 45 degrees, opposite over hypotenuse, I get 1 over root 2. Cosine of 30, back to the other triangle. Remember, 30 degrees is the same as pi over 6. And that comes out to be root 3 over 2. Minus cosine of 45, adjacent over hypotenuse, times the sine of 30 degrees. I guess I could show the triangle. It's up here. Pi over 6 is 30 degrees. Sine is opposite over hypotenuse. So that's times 1/2. And notice the denominators are the same. Root 2 times 2, root 2 times 2. So I think it looks better if I wrote that as 2 root 2. And I have 1 times root 3, which is root 3, minus 1 times 1, which is 1. Could this answer be cleaned up by multiplying top and bottom by root 2? Absolutely. But we'll just leave it the way it is for now. Okay. You can do something like that. Here's another one. 255 degrees seems like sort of a random angle. But we can actually find the value of the cosine or the sine, really, of 255 degrees using this identity, using the angle sum or angle difference identity. Let's do this how we've been trained. 255 degrees, we need to figure out what quadrant that puts us in, and we need to know the reference angle. I showed you how to do it on a previous video in terms of radians. We could certainly convert that to radians, but let's just keep it in degrees. It's the same idea. So if you start here, that's 0 degrees. You go halfway around the circle is 180 degrees. So to get to 255 degrees, I can either go forward by, what would that be? 75 degrees, right? If I add 75 to 180, that's going to give me 255 degrees. So it puts me in the third quadrant, right? It would have been further to go backwards from 360 degrees. 75 degrees is less than 90. So I can tell that this is going to put me in the third quadrant. And remember how it works, just like when we use special triangles, finding the cosine of 255 degrees, I can just work with my reference angle of 75 degrees. And because all students take calculus, the only thing adjustment I'd have to make is I know cosine should come out to be negative in this quadrant. So the cosine of 255 degrees should just be the same as the negative of the cosine of 75 degrees. And 75 degrees happens to be the sum now of 45 plus 30 now, instead of subtracting like we did to get 15 degrees. So using my identity for cosine, with this being A and this being B, and I'm going to put a big bracket around this. My identity is cosine A, cosine B, which is 30 degrees. Let me put this here below. So I'm using this one down here. When I'm adding, I actually then subtract now. So it's going to be minus sine of 45 degrees times the sine of 30 degrees. We've already done the triangles for these. This is 1 over root 2. Cosine of 30 is root 3 over 2. Sine of 45 is also 1 over root 2. Sine of 30 is 1/2. And I end up with negative quantity. Very similar looking answer. The denominator is still 2 root 2, and I have root 3 minus 1 times 1, so minus 1. Again, that could look different if you decide to multiply top and bottom by root 2 to rationalize it. So same idea, but another way of getting you to think about that identity is, what if I said to simplify this expression? So then the idea is 100 degrees and 10 degrees. Those aren't angles we know how to find the cosine or sine of, but it has the form. If you look carefully, that has the form of cosine, cosine, sine, sine, cosine, cosine, sine, sine. There's a plus in between here, so this actually must be the formula for the cosine of A minus B, where A is 100 degrees and B is 10 degrees. So it's just the same. It's the right side of this identity. So this would be equal to the cosine of 100 minus 10, which is the cosine of 90 degrees, and the cosine of 90 degrees. 90 degrees is up here on the unit circle. The point is 0, 1. Cosine's the x coordinate, which is 0. So this whole expression right here actually just equals 0. All right, in the next video, we're going to look at what we call the double angle identities. So make sure you check that one out.